Our next speaker is Jorge Toledo Marin. So Jorge is a sociologist from Havana, Cuba. He is a committed scientific diver with experience in film and radio production. Jorge is in the class of 23-24. Jorge was also admitted to the cohort of 22-23. Jorge was also admitted to the cohort of 21-22. And his visa application got placed in sort of administrative limbo. And so we've been talking to Jorge since, I went back and looked, like December, maybe 2020, February,
Yep.
A long time, trying to get him here at Scripps. And he has remained so committed over all those years of finding a way to get here. And we were equally committed to finding a way to get him here, and we're just so grateful he finally made it. He made the most of his time while he was here. He became a science diver, did the photogrammetry workshop all week last week.
That was really cool.
I think you did the boating class.
Yes.
What else did you do? He made a very, very unusual film this summer that I encourage you to check out on our YouTube. And really just an integral part of the cohort this year. So glad that Jorge could finally be here, and really just, I hope you don't have to leave. I hope you find a way to stick around for a while. The name of his presentation today is Electric Oceans, the Impact of Offshore Wind Energy on Marine Life. Welcome, Jorge.
Thank you very much, Samantha. Thank you. Okay. I want you to think about the first thing that comes to mind when you picture a marine underwater environment. Because to me, it looks something like this. This is why I learned to dive back home in Havana, Cuba. It was all clear blue waters, lots of mist. And this is what my regular dives looked like until I came to Scripps. Yeah, that's a pretty bad day. I should have stayed back home. No, I'm joking. Learning how to navigate is one of the most important skills to learn as a diver, because when you're down there, you're confronted by a world in which visual cues are often limited or completely absent. And the persistent currents are always trying to keep you away from your path. That's why aquatic environments are the most challenging places in the world for navigation. But no matter how challenging it may seem to us, many animals complete like really long journeys across the ocean, like the white shark that swims about 10,000 kilometers between Africa and Australia. Don't look at the map. And that was, and like the Pacific salmon was able to return back home after years out in the ocean. The bluefin tuna migrates between the Atlantic to either the Gulf of Mexico or the Mediterranean. So how are they able to complete this incredibly crazy long distance journeys? Well, since the mid-90s, wait, sorry about that. They use a range of sensory cues from wave movements to Earth electromagnetic field. We still have a lot to learn about the physiological, neurobiological aspects of how they do this, but there are many studies suggesting the use of specialized organs among a specific subclass of fish known as elasmobranchs. Elasmobranchs are sharks, rays, and skates, and all share common features, but one stands out: a unique sensory system known as electroreception. With it, they can detect electric fields generated by, for example, the muscle contraction of prey, and navigate by detecting Earth's magnetic field. Or so we think. We still don't have concrete evidence for this, but since we know they can detect the on and offset of weak magnetic stimuli, we think they might be using this sixth sense for navigation purposes. But as if finding your way in the ocean under normal conditions wasn't challenging enough, human activity can often impose or create scenarios where this becomes more challenging. For example, offshore wind farms. Offshore wind farms are a great way to generate cleaner and renewable energy that not only contributes to addressing climate change, but also helps us in securing our energy demand. But there might be certain aspects that we need to address. For example, the construction process can create significant vibrations and noise, the physical structures themselves may pose risk of entanglement, and the EMFs produced by the transmission cables may become invisible yet challenging obstacles for marine life. But what exactly are EMFs? Well, the power generated by offshore wind farms needs to be transported back to land via cables, right? Electromagnetic fields, or EMFs, are like invisible waves that are generated whenever electricity is produced. So think about it as ripples you see in the water when you throw a stone on a lake. The ripples spread out from the source and bounce on the edges. And then they spread back in, bounce onto other ripples, creating more distortions on the surface. In our case, the stone is the electric current flowing through the cables. It's the cause. And the ripples they're creating are the electromagnetic waves that flow onto the surrounding areas, creating distortions. And because offshore wind farms and the turbines themselves can be very big, much bigger than the land counterparts, they can generate a lot of power. To give you a sense of this, 1 megawatt can power about 300 American homes. One land turbine can generate around 6 megawatts. So that be enough to power about 1,800 homes. Offshore power can power 4,800 homes. So it makes it a lot more efficient than land farms in many ways, creating a lot of power and a lot of EMFs. So if elasmobranchs are relying on the natural ripples of Earth's magnetic field to navigate, how are man-made distortions in it affecting their abilities to interact and read their environment? To address this question, a series of controlled experiments were carried out by Capstone Advisory Co-Chair Cal Newton. So the experiment involved 2 types of skates, the long nose skate and the big skate. Our experimental setup involved a merit coil system, a high voltage cable, 2 types of stimuli, GMF and EMF, and a data collection process. The merit coil system is the cage-like structure you see to your left, and to your right, viewed from top, the water tank where the skates are placed in this experiment. This is our actual setup. The cage creates a magnetic field that tricks the skates into thinking they've been displaced, say from north to south or vice versa. And what we want to observe is how it reacts. Does it orient itself back home? Does it behave confused or disoriented in any way? To register this, a high-definition camera is placed on top of the tank to record the skates. And the software tracks their movements to produce the data we analyze. I want you to remember this video for when we go over the heat maps. So, for our project, we established 2 goals. The first one was to set a baseline for future analysis, to explore the impact of the experimental setup itself. And the second one, to create an outreach tool to communicate and share the results of this research. Objective 1, data analysis. What do we expect? So when we expose the skates to EMFs, we would expect to see an alteration in their behavior and navigation patterns. However, since our aim was to establish the baseline, we only analyzed 2 variables, control and procedural control. And I'll explain this in a little bit. But understand that with these settings, what we would expect is to see no change whatsoever. And that would be a good thing, because it means our experiment works. And it's great, because it's exactly what we found here. Here are 3 box plots showing the big skates data for 3 variables, velocity, acceleration, and body angle under our 2 conditions, control and procedural control. But what does our procedural and control look like? Well, follow me here for the sake of argument. Let's say instead of testing the skates for EMFs, we're testing them for light. And because I don't have a fancy lab, I just have them in my room, okay? They're just hanging there. So I go ahead and I turn off the lights to register the differences in behavior between a brightly lit room and a dark room. But I'm not satisfied with this, so I go even further and I take out the fuse box in the basement so that there isn't even the potential of light here. That is our control. Our procedural control involves putting the fuse back in. We want to see if the skate is able to react this tiny change in the environment. Are they able to sense that something different has happened? And as we can see here, back to our plot, they are not, which is, again, great news. Not in terms of velocity, acceleration, or body angle. No significant difference was found when we ran these tests. This is great news. The long nose skates, we tested under the same conditions, and no changes were found here either. We do see, however, a change in terms of behavior between species. There's less concentration of data points here suggesting that this skate, the long nose skate, was less active. Whereas the big skate might be swimming around a lot, this one remained stationary most of the time. And this is an important distinction, as the potential impacts of EMFs on marine species will vary not only between species, but sometimes we can see differences between individuals. Here are our three big skate subjects. Big F1 stands for big female one, big male one, and so on. These heat maps show the spatial distribution over time. Remember the video I showed you? Yeah? Okay. If not, I got your back. Okay. So this is what we're seeing here. The brighter areas show where the skates spend most of the time. When I first drew this, I saw the big F1 and M1 somewhat behave similar to here, somewhat uniformly distributed, but seemed to focus on the southwest corner here. And I thought, oh, there's something interesting. But along came big M1 and just did the exact opposite. And these are just normal differences we see between individuals. These are the heat maps for the long noses, and we can see what we've already established. There's differences between species, and we're not registering significant differences between our control and our procedural control. Before I ran any statistical tests, I obviously plotted my data to visualize this. Early on, I created these heat maps by sex, both species combined. And as you can see here, the females show no differences between conditions, but the males seem to be a lot more active here. So when I saw this, this suggested to me that perhaps males were more active, so maybe looking for prey or mates. But when the slightest change in the environment was detected, they would stop, making them less active, more sedentary, and perhaps less likely to find a mate and more likely to become prey themselves. The tests prove this to not be the case. We've already established that there's differences between species. Our sample is small, power is low to conclude anything of the sort. However, visualizing the data allows us to consider ideas like this and test them. I don't have any more time to show you any more of this, but if you want to learn more, you are in luck, because our second objective was a communication tool. We created an outreach tool to communicate the process and results of this ongoing research. And for this, we developed this brochure that I have right here with me, and you can all get one if you look under your chairs. No, I'm joking, there's nothing there. But you can find them outside. But I'm glad you're paying attention. All right. A final version of it will be distributed at the Oregon Coast Aquarium during its Elasmo Bank Week next month. And because we wanted to make this information available to a wider audience, like for example, my parents are right over here, we created this version in English y esta en español. Con la misma información dirigida al público hispanohablante, el folleto cuenta con un enlace a una página web donde se puede encontrar la misma información detallada sobre la investigación. All right. Both link to a story map in English y español. It provides information that cannot be confined to the strict boundaries of a trifold, but it has a full description of the project, and you can see where the areas of long nose skate and big skate overlap. You can scar the QRs in the back here, and I'll leave them up here at the end of the presentation. But first, I don't know how I'm doing with time. Okay, almost there. I want to start wrapping this up by acknowledging the importance of offshore wind farm as an important source for renewable energy, especially in the context of rising temperatures and increasing global demand for energy. Offshore wind farms' potential impacts on marine ecosystems should not halt the development and pursuit for this energy source. Any action we take or refrain from taking will inevitably impact our environment. There's no one easy fix. But this is why research like this is important, so that the policies we draft are the most informed and the technologies we develop are done with the best available science. Understanding marine ecosystems will allow us to minimize those potential impacts. And before I let you leave to the next wonderful break, I want to take a minute to acknowledge the people that not only made this project possible, but whose support allowed me to become a part of this program in the first place. So Samantha already mentioned that I've been trying to get here for a while, and Samantha has my back from the beginning, so I really want to thank you. I'm really grateful for all your support. But a project this school wouldn't be possible, it wouldn't be a one-man show, so I want to thank also the man, the myth, the legend, and my best friend, Dr. Greg Rouse. Okay. Who else? Who else? Okay. Obviously, congratulate the entire MSc program, Hannah, the cohort, the awesome people, the awesome people at the Dive Locker, the Scuba Diversity Fellowship, Aburto's Lab, Dominique, Lauren. I know this is not a award ceremony, but I really have a lot of people to thank. From ICO, Gabriela, my PC mentor, Fernando Melendez, and all the labs that allow me to dive with them throughout this year. Thank you very much. And finally, my capstone committee made up of these three outstanding citizens. Amazing Dovie Kossev, the spectacular Kyle Newton, and the great Mark Danielson, my new best friend, our studio, and of course, Walter the cat, which is Kyle's cat. So thank you very much. Any questions?
Okay, I have a question.
All right.
Let's see. If elasmobranchs navigate and hunt using EMF signals, are they already being impacted by all of our satellite, radio, and other waves?
That's a great question.
Thanks.
Unlikely. Yeah, these are like very far away. Set you up. That's very unlikely. I'd want to create the idea that the cables, that as offshore wind farms expand, the cables are just like destroying the underwater habitat. The electromagnetic fields tend to dissipate after a few meters. The reason this is interesting is because we still don't know how they manage to interact with Earth's magnetic field. So that's a scientific question of interest. How do they do it? And as we expand into offshore wind farms, it's also relevant because how will they then be impacted by it? But the idea of them being impacted by satellite, it's very unlikely. They have to travel through water and so on. So no.
Why are offshore wind farms so much bigger than their counterparts on land?
Great question, Samantha. Thank you very much. Well, they're much bigger because it's one of the main reasons. Just turbines in general are very big, and getting like huge blades up into like the mountains or wherever they're going to be installed through the narrow roads is very challenging. Whereas offshore, you can have like the factory right on port and carry them into ocean. Also, the winds are most consistent and strong in the oceans, so you can take advantage of that and create like bigger wind turbines.
Great. Thank you so much, Jorge.
Thank you all. Enjoy the break.
We